Good afternoon, everyone. Let's begin. Thank you for coming to this talk. My name is Adam, and today we would like to talk something about internals of exceptions. So let's actually start with this slick slide showing us an excerpt from Microsoft documentation from MSDN. And this is an excerpt telling us where and how can we use exceptions. And it mentions the thing called exceptional situations. And in this talk, what we are going to do is we are actually going to see what those exceptional situations are, how they work under the hood, and why they may be very tricky to handle. We won't be talking about simple things. I generally assume you do understand that there is try-catch finally, that you can specify exception types and all those things. Today we'll focus on other things like situations when our finally blocks do not execute, when someone tries to kill our application, when we get Stack Overflow, and when we get access violation exception. So those situations we typically do not consider when we do write our applications, but still sometimes they happen, and we need to be able to handle them correctly to preserve the user state, to avoid any more impacts on the state and breaking the application even more, and finally to safely carry on. So my name is Adam Furmanek, and please join me in this tour of internals of exceptions. So before we begin, a few words about me. I have been a .NET developer for over 5 years. Now I'm a big data, Scala, machine learning guy at Amazon. So I do personalization in Amazon Prime Video. I'm also a blogger and a public speaker. Feel free to take a look at my blog at blogadamfurmanek.pl. Also drop me a line on Twitter or email, whatever works for you. Earlier this year, I also released a book called .NET Internals Cookbook. If you are interested in .NET internals, like about GC, memory management, synchronization, logs, all those things, feel free to take a look at this book. It's like 100 questions and answers about various aspects of .NET platform. Okay. Let's go. This slide deck will be available for you at the very end. There will be a QR code so you can download it easily. Also, feel free to drop me a line if you would like to ask any more questions regarding this talk or whatever else. So agenda for this talk is we'll have actually 3 significant parts. As I said, I do assume you understand exceptions more or less, so we'll try to dig deeper and see how all those things work under the hood. And we'll see multiple technologies today, not only C# but also intermediate language, C++, WinAPI, some low-level mechanism. We will generate some machine code. We will see how those things work across platforms, across operating systems and architectures. So 3 different parts. In first part, we'll actually see the mechanisms which we are going to cover for today. So we will see how they look like very simple snippets of code, what they present. Then we'll take a look at the internals, but from the high-level point of view. We'll see how those things work in those edge cases, in those situations which we typically don't consider when we do implement our applications. And in the last part, we'll see how those things are implemented under the hood, how this works on a CPU level or on the architecture level. So let's go. Let's start with exception mechanisms overview. And the first thing we are going to cover is basically C# and C++. So C#, I presume you do know, there is try-catch finally. There is a full syntax on this slide, even with exception filter, which we'll cover a little later. However, on the left side of this slide, what you can see is C++ equivalent of exception handling. Interesting thing here is there is no finally. Even though it's very similar platform, at least at the first sight, it's completely different because it doesn't support the finally block. So how do we implement finally in C++? And in C++, what we do is we use the pattern called resource acquisition is initialization. The way it works is we do allocate some object which is allocated on the stack and has a destructor. Whenever the stack we start unwinding the stack, we exit the function and we need to remove that object. The destructor is being called. So that's the point when we can actually execute some code, and the destructor works as a finally for us. Apart from that, catch is very similar to C# syntax, so you can see that we do specify some exceptions. So more or less very similar, nothing surprising here. But if we start going down, and if we take a look at, for instance, IO handlers in intermediate language, what we can see is C# has almost everything from the IO language. There is one more thing added to IO, which is called fault handler. It's very similar in nature to finally block. in the sense that it executes often, only the difference is that finally executes often no matter what happened in the method, whether there was an exception or not. Fault is being executed whether there was an exception, no matter whether we handled it, whether we ignored that exception, fault is always being executed. Apart from that, we also have try-catch finally, and we do have the exception filter, which we'll cover a little later, and we'll also later see how those things are implemented in C# using the constructs you can see in intermediate language. Let's go down, and what we can see when we take a look at like under the hood on lower level system mechanism is we do have two mechanisms which we'll cover in details today. First of them is called structured exception handling, SEH. And the way it works is, you can see it on the right-hand side of the slide, is we can have try with exception block with catch block, or try with finally. We cannot have try, catch, and finally in like one block of code. But the difference with exception handler or with the catch handler is that we do not specify the type of the exception. What we do is we provide the so-called exception filter, which is different but similar in nature to exception filter in C#. So let's see this in action. Can you see the code at the back there? Raise your hand if you can. Lovely. OK, so what we are going to do is we do have a very simple C++ application, which we will see in details. First, structure of the demos, which we'll have today. Generally, we'll have some code which we'll start analyzing from the bottom. There is probably some main function. We'll go up through some functions, till we get to some code generating exceptions, something simple like throw or generate division by 0, whatever else. And then we start analyzing the application going from top to the bottom. So we start in here in this main. We call method try, which has try and accept block. And in accept, we provide the filter exception method. And then we get in this try method, we call the generate exception. So what we do here is we do generate division by 0. Now what is happening? Normally in C# or in C++, we would specify here in this place the type of exception we want to handle. What we do here is we specify the method. This method is supposed to answer a very simple question. Operating system comes to this method and asks, hey, what do you want to do with this exception? And this method can return one of the three values. So two values are pretty simple. I don't want to handle this exception. I don't care about it. I don't know it. So please go else, find someone else who can handle this. Or the other value is, yeah, I do know this exception. I want to handle it. But there is third value, meaning exception continue execution, which basically tells the operating system, hey, I think everything is fine. Let's just try again. And this is what we are actually doing in this simple sample code. We do divide by 0, and then we have a counter which we increment, and we check whether it's below 10. If it is below 10, we tell the operating system, hey, everything is perfect, try again. So what operating system does now is it executes the last instruction again. It restores all the registers, restores the state of the application, and reruns the instruction. This instruction is here. It's 1 divided by 0 again. So we get exactly the same behavior for the next time. So we do continue for the first time, for the second time, for the third time. And every single time, we get the division by 0 exception. So after 10 times, we finally decide that when this if does not execute, then we tell operating system, hey, I want to handle this exception. So we return the code saying, hey, execute the handler. And at the very end, we execute the exception block, which is here called __ except. So now we can see that even though this mechanism is very similar to what we have in C# or C++, we actually have this third option which we can use to do something else. Also, it's worth noting here that this method filter exception is executed always, no matter what the type of the exception was. We don't declare the type we want to handle. We only want to provide the callback, which is called by the operating system. Let's go back to the slides. There are two more mechanisms in Windows, very similar in nature, which we'll cover today. They are called vectored exception handling and vectored continuation handling, VEH and VCH. They are very similar to signals in Linux, and the way they work is that they are not contextual, to the opposite as the normal try-catch block. So what we do have in our second demo is we need to register handlers for exception handler and for continuation handler. So we just just tell the operating system, hey, if there is an exception, call this method, no matter where this exception happens, where exactly it is being thrown. So again, we call method try. In method try, we call generate exception. We do some division by 0. Now this exception is being thrown. It's worth noticing here that we do have SEH installed as well here. We do have try except block. But the VEH handler has a priority. So it is being executed first. So what we can see is we are in VEH exception handler method, which is basically here. And here again, we want to return to the operating system the special code telling it what to do. And the interesting thing is we have access to all the registers and all the state of our application at the point of executing the instruction which calls the exception. So here we have a structure which we can actually use to traverse the registers and modify them. And we'll use this in one of the next demos. But what we do here is we do division by 0 by dividing 1 by this variable, which we can modify. So what we do in this handler is we modify this variable to 1, and we tell the operating system, hey, it's perfectly fine to continue. Just try again. Operating system now what it does, it resumes the execution at the last instruction, and also it calls the continuation handler, which is called only when we told the operating system to continue. So this handler is now being called, and we execute the last instruction again, but this time we have completely different effect, because previously we were dividing by 0, now this variable was modified and set to 1. So we don't get the division by 0 exception anymore, and we can safely continue. So as you can see, we are entering try, and then we do execute VEH and VCH. We do not execute SEH handler at all, and then we just exit try. Everything continues successfully. So those are mechanisms which we will be covering today. There are some more mechanisms which we could discuss. One of them is called dwarf, which is similar to SEH in its nature, only it's table-based. SEH is also table-based depending on architecture. We'll see that later. And there is one more approach, very basic when it comes to exception handling, which is called set jump, long jump. And we'll see it at the very end. The basic idea is we do set jump, which is basically we store all the registers, the context of our application before we start executing some line which may cause an exception. And then when something wrong happens, we do the long jump to the place where we were when we knew something was good, when we knew the state was correct. So this is what we'll cover later during this talk. And now comes the question. Actually, one more thing. If you have ever seen a window like this in your operating system, now you know what this third button means, continue. Typically, when you click it, this window pop-ups again because nothing happens, like you don't change the state. But in theory, you can continue and modify the state, for instance, by calling some handlers. OK, so we started with assumption that we more or less know how exception handlers work, how try-catch finally works, etc., etc. So if you feel like you understand exceptions, then you probably may want to answer some of the tricky questions about exception handling. And this is only a subset of questions you may want to ask yourself. And those include things like very edgy edge cases. For instance, what happens when you try killing the application? What happens when you get Stack Overflow? What happens when you get, like, out-of-band exception from some different thread? What happens when execution engine exception comes in? And all those things we typically do not cover when it comes to handling exceptions. And in this talk, what we are going to do is we will try to answer some of those questions at least. And what's more important, we will try understanding how those things work under the hood. So this concludes first part. Let's move on to implementation details. So let's start with a very simple thing. One of the questions was, what happens when we do exit application? Is the finally block executed at all? And interestingly, oddly enough, it depends on the platform significantly, and it can differ also depending on the way how we exit the application. So in C#, when we call environment.exit, finally blocks are executed. But when we try calling environment fail fast, or when someone tries to kill our application and all those things, finally is not being executed. What's worse, when we do have StackOverflowException, our application is being killed immediately. And we cannot stop that. We cannot handle that at all, which is pretty nasty, because now you can imagine that you are running some unit tests, and one of your tests has a bug because it throws Stack Overflow exception. What happens then? Your whole test runner just dies. Your tests are not executed anymore. You have no logs, you have no stack trace, you have nothing. It just dies. You cannot do anything about this in C#. We'll actually see later how it worked before and if we can do anything about this. But general rule of thumb is we are just doomed in that case. In SEH, finally is not being executed. In Java, it is also not executed, but it also depends because we can configure this depending on the permissions we have. It may work, it may not work, but thing is interesting that in Java, you can handle StackOverflowException easily and just carry on. So Java is like, allows you to do this thing even if this terrible thing happens, like StackOverflowException, Java just allows you to go on. Okay, that was simple. So let's start with typical thing. We do handle exceptions. What we typically want to do is we handle them. We want to log some state or log a message that, hey, something wrong happened. Then we just rethrow this exception so it's handled like above in some layers on the top and probably returns some code to user or whatever else. So the question is, how do we rethrow exception the correct, the right way? So let's go through this very simple code. Once again, we start from the bottom. So we have some main where we call the method. Then in this method, we call method throwing exception twice. But we do have try catch. And in that try catch, we want to rethrow the exception. And you probably do know that if we replace line 27 with throw E, it's not the right answer. What we see on this slide is in bottom left corner, you have the output that you would see in your console, meaning printed out to your output. Bottom right corner shows you what you see when you start debugging application using WinDebug and you dump the stack trace as seen by the CLR thread, so on the low level of the threading platform. So we can see that only two lines are indicated here, only the line calling the method and only the line throwing the exception. So this is not what we want because we just lost the source of the exception. We don't know where it was exactly thrown and why. Also, CLR stack command shows us nothing. So can we do better? Probably the typical answer you know is instead of doing throw E, just do throw. And it works better, indeed. We can now see that the exception was thrown in line 10 at the top, and it works generally pretty well. The only thing here is, can you tell me whether the method we called, which ultimately thrown the exception, whether we code it in line 17 or 18? In this sample code, you probably can do it because it's super simple, but you can imagine there is some if condition, there is some loop, there is some state in the play, so the code is not necessarily like deterministic. So where did we exactly code this method? And this is the answer which you typically see in the books, just do throw and you are good to go. And as we can see, it's not necessarily perfect because we would like to have this line. So can we do better? Can we somehow get this line and print it out so we know where we exactly code the method? Maybe instead of rethrowing the original exception, let's try something different. Let's throw new exception and pass the old one as the inner exception. It works. As you can see, we have all the lines in bottom left corner, so all the lines are highlighted. They work pretty well. The only problem here is originally we thrown a system argument exception, but now we are throwing system exception. So we changed the exception type. We significantly changed the behavior of our application, probably introduced some bug by making this line of code. So while it is better, I mean, we do have this line and that's what we wanted, we probably broke the application, which is definitely not a thing we'd like to do. So can we somehow get all the lines in the output and still capture or continue with the same logic? And there are actually two answers to that. First one is based on some low-level trickery with reflection. You had something called .NET remoting previously in .NET, which was thing basically you could do RPC across processes. So you could do some network call, which seemed for you to be like a local call. And now if you actually do the reflection trickery, what you can do is you can prepare the exception for remoting, and then you can call the method which you can call this exception and throw it again. So what happens now is you do have all the lines of code. You do have all the lines highlighted, so it works well. You do have the same type of exception, so it works well. The only problem is, or maybe the only drawback of this approach is you are using some nasty reflection. So now if you submit this as a code review or as a pull request, probably your reader will start asking questions, hey, why not just throw semicolon? So maybe it's not the way to go, not to mention that reflection may give you another exception that you have no permissions to call this method. So while it may work, it may actually introduce even more problems. But there is a good way how to do it. And this way was introduced with .NET 4.5 with C#5 when async was introduced, because in that case we had a lot of use cases when we had an exception in some different context, probably on different thread, probably executing somewhere else. So we had to capture this exception and rethrow it by preserving the stack and everything else. So what was introduced was exception dispatch info, capture and throw. So we do capture the exception and we restore the data. And starting .NET 4.5, this is probably the best way to rethrow the exceptions. Just capture them and rethrow them like this. And this is what is actually being done by the .NET platform under the hood when you do use async await, so it's not a black magic trickery which you should never touch. However, it's slightly longer than just throw semicolon. Okay, so we started with how we want to handle exceptions. We want to log something and probably rethrow them. So now the thing is how to handle everything, yes? So how to catch everything. In C++, it's super easy, just use ellipses. In SEH and VEH, it just works because the exception filters are called always. Operating system just asks you, hey, do you want to catch this or not? So it's called for all the exceptions. We do not declare the exception type. In .NET, things become tricky again. So depending on the .NET version, in like very old .NET version, .NET 1, we had different behavior when it comes to things which do not inherit from system.exception. We need to remember that there are other languages on .NET platform. For instance, one of them is C++ CLI, which is basically a managed version of C++. And in that language, you can throw anything. You can throw string, you can throw exception, you can throw integer, you can throw whatever you want. So what was happening in .NET 1 when you throw something like this, it wasn't wrapped with any exception. So what you had was you had two exception handlers. One of them was catch exception, one of them was catch with no type specified, and the latter handler was catching those exceptions. In .NET 2, they changed this behavior. Now those things are wrapped with a runtime wrapped exception. This broke the compatibility slightly, so there were attributes to fix that. But generally, this is the way to go right now. We do catch exception or catch without specifying the type, and it should catch everything. The answer in Java is we can catch throwable. It should catch everything, including memory errors, including stack overflow exceptions, etc., etc. The only question now we should ask is, do we really want to catch everything? Because believe it or not, there are platforms which do use exceptions to control the flow of your application. One of them is, for instance, Scala. In Scala, there is no break keyword. Whenever you have a loop and you want to break, there is no break keyword. The break is just a method which throws an exception. And there is completely different branch of exceptions in Scala, which is controlled like flow control exceptions. So you should never catch them unless you want to break the Scala language, because if you do try catch and then you catch this exception, the break keyword or the break method stops working. So generally, catching everything may not be the best idea. Also, because developers were catching everything, .NET and Microsoft actually changed the internals and stopped or blocked the possibility to catch a lot of things in .NET. We'll see that later during this talk. But the reason why it was changed is because people were catching those exceptions, but not necessarily thinking how to handle them correctly. Okay, so we know how to catch and rethrow. We know how to catch everything. Now the opposite. Are there things which we cannot catch? And obviously there are. There are uncatchable things in .NET, so things which we will never catch. One of them is already mentioned StackOverflowException. Other things are, for instance, thread abort exception. While we can catch it with try catch, we cannot just swallow it. In order to swallow it, to get rid of this exception and stop it from propagating, we need to call the reset abort method. And that's the way to handle it and swallow it. But there are other exceptions. One of them is, for instance, access violation exception. Depending on how it was thrown, we may or may not be able to handle it. There is also a much more severe exception called execution engine exception. Raise your hand if you have ever seen that. Oh yeah, I do see some hands. So generally, if you do have exception like this, execution engine exception, you probably have much bigger issues than just not handling this exception correctly, because then nothing may work in your .NET platform. And there is also out of memory exception, which may or may not be able, which we may be able to catch depending how it was thrown. And there are also some generic exceptions, like SEH exception is the exception thrown by the SEH mechanism, which we have already seen. This exception is thrown when we do not map it to some .NET managed exceptions. So generally, there are a lot of things which we cannot catch at all. So now the thing is, OK, if there are things which we cannot catch, so can we at least tell when those things will be thrown? So when are those exceptions thrown? And like obviously there is one simple scenario, which is do throw something, then exception is being thrown. But there are also exceptions thrown in so-called out-of-band manner. So those exceptions are being propagated outside of the normal flow of our application. And typical scenario when we do see those exceptions is when we play with async and await. So let's actually see a demo how it works with async and await. So let's do the demo code exception in async. Let's make it as a startup project and let's run it. So what we do have here is, OK. We do have a main method in which we do have try catch, and we call method throw twice. And then we do some printing. We sleep for 900 milliseconds. We sleep again, etc., and print again. What we do in this method is async void, something you probably should never do. And we do await task delay, and then we throw exceptions. So what happens is we do throw, and this method waits 300 milliseconds and throws the exception. And what we can see in the output, like apart from the fact that our application crashed because there was an unhandled exception, what we can see here is, if we do close this window, we can see that exception was thrown, but also the 2 lines after the exception, after this method which we called, those 2 lines were executed as well. So we did print out after sleep and done. So it seems that our application safely continued. So, however, if we do introduce some random sleep in the middle, so I do introduce thread sleep here. So first thing we may want to actually think about here is that, hey, we do have this throw method which waits for 300 milliseconds, but then we sleep here for 600 milliseconds. Shouldn't we catch this exception? Well, the fact is we cannot catch it here because it's thrown in this out-of-band manner, so it's thrown outside of this normal execution context. And what happens is the application crashed again, but this time we do not have those 2 lines executed. So just by introducing random delay into our application, we significantly change the behavior of the code, and we don't continue now safely. The application just dies and doesn't execute anything else. So this is when we call async void method. What happens when we execute async task method? And the thing here is, even though we do not await this method anymore, what is happening here is exception thrown in this method is propagated and handled by the state machine of async and await. And then it's stored on the task object and not propagated anymore. So actually, the question is it better than what we had before? Because before, we had an exception which was thrown, propagated out of bounds, but at least we knew there was an exception. We observed the exception. Here, in this situation, the exception is basically hidden. It's not visible for us anymore. So the exception is stored on the task object. And the thing is, when garbage collector starts cleaning the memory, when it notices there is a task which it needs to be cleaned up, and this task has an exception, then GC starts propagating it. And depending on the version of .NET we are using, whether it's .NET 4, 4.5, or something later, the behavior differs. It may crash our application. It may not crash our application. It depends. But generally, we can also handle the exception by calling the unobserved, or actually we can register a callback for the exception, which is called unobserved task exception, which is very similar in nature to first chance exception, for instance, on app domain. So the takeaway here is async void methods, they do propagate exceptions out of bound. Generally, never use async void methods unless you are forced to. And also, the problem with them is you cannot await them easily, but it's possible to await async void methods. And with async task methods, whenever you use them, always await them. If you do not, at least have this handler, otherwise your exceptions will get unnoticed and will run away. OK, so now we answered the question, when are exceptions like thrown? The thing is, can we ask .NET, hey, stop throwing exceptions on us. Please do not throw anything for us. And the answer is we can do this. And the thing is, it's called constraint executed region. So whenever we set up a thing called constraint executed region, we tell the .NET, hey, we don't want to have any exceptions in this part of code. What .NET does after we ask it for this thing is it prepares the special block of code, it compiles all the methods using JIT compiler, it checks whether we have enough space on the stack, this allows us to use, for instance, locking and some other methods, but generally then .NET tells us, hey, I probably won't throw any exceptions on you. I don't guarantee that, but I will try to do my best to not do so. So generally, we can ask .NET to stop propagating the exceptions, and the way we use it is we need to use it with try, catch, and finally. The interesting thing here is as constraint executed region is only in catch and finally block. So typical pattern you will see in the code base is you do have try finally with empty try block and all the code being in finally. Your ReSharper plugin will tell you, hey, this try finally is not needed here, just remove it, and then you break constraint executed region, so beware of that. So this is how we can stop propagating the exceptions. But now the thing is, we have already seen some exceptions being propagated in the out-of-band manner. What happens when we throw exceptions on other threads? And the thing is, in .NET, it really depends on the version again, depending whether we use very old .NET like .NET 1, whether we use .NET 4 or .NET 4.5, whether this exception is being thrown on thread pool or normal thread or whatever else, the exception may or may not kill your application. But general rule of thumb is whenever you do create a new thread and you don't handle the exceptions, it will kill your application. So unhandled exceptions on threads, they do kill your application immediately. And the thing is, you cannot do anything about that. Not only your thread dies, but the whole process dies. And you cannot stop it even when using like first chance exception handlers on updomain or whatever else. This is just how it goes. It was different in .NET previously, and it cannot be changed now. The thing is, can we somehow stop the threads from being, stop the process from being killed when an unhandled exception is being thrown? And the thing we can do here easily is, or at least we can do, maybe not that easily, is we can modify the thread constructor to handle those exceptions. So let's see another demo, which is called thread exception handler. Let's just run it. And what we are doing here is we do have create new thread, which uses this piece of code which runs this piece of code. And this piece of code is just telling us that it's running in new thread and throws some new exception which is unhandled. What is happening here is we would like to somehow handle this exception, because otherwise, if we don't handle it, it kills our process. What we can do is here, we just use that new thread constructor. We can modify the code of this constructor by generating some machine code under the hood. So what we do is we generate code like this, which basically takes the original thread constructor code, jumps to some other place, and then calls our method by doing the jump here, which basically does a very simple thing and changes the lambda which we originally passed to the thread constructor with this try-catch handler and calling the lambda. So what is happening here, first we hijack the thread constructor to introduce our own machine code to do the magic. We then call this method, and when this thing is being called, it effectively calls the thing here. So we take the original lambda which was there and which we call here the thread start, and then we wrap it with try catch, call the method, and when the exception is being thrown, we can just catch it easily here. So as we can see here, not only the exception was printed out, but also we are saying that all done, that everything worked correctly. So this all done is being executed in line here. So while it's not that super simple to handle those exceptions, there is a technical way to do this. Obviously, this is not something you should do in normal production code. It's only when you, for instance, have really severe situations that you cannot modify those threads to handle exceptions on their own. For instance, if you do use IKVM, which is a Java implementation in .NET, .NET implementation of Java Virtual Machine, you can run the Java code directly. And because in Java, exceptions, unhandled exceptions on threads do not kill the process, Java programmers don't necessarily handle them with global try-catch. So if you do run this via IKVM, then it will kill your process here. So this is how you can avoid doing that. The same problem may be actually with, for instance, if you use MEF or MEF, so extensibility framework for loading plugins. If you do load some code which you don't control, the programmer, the owner of that code, may actually introduce a bug into your application just like that. Okay, So that was constraint executed region, and handling and rethrowing and seeing how to handle exceptions and all those things. And this concludes the second part, how those things work like from the behavioral point of view. So now let's see how those things are implemented under the hood, how they work like on the lower level. So let's start with how do we see exceptions like in WinDebug. Whenever something happens, and when we do have an exception handler being called like SEH or VEH, what we do have is we do have a structure explaining or describing the exception which has been thrown. And this structure actually has two important pieces. First of them is the exception type, because we do know what exception type is because the CPU tells us that. It's not that division by 0 goes like unrecognized, that we need to figure out whether it was division by 0 or not. CPU is being kicked out by like memory management unit or by FP unit of calculations or whatever else, and it has the exception type, so it knows what is happening. Different interruption is being used. So we do have this code, and it's magical number telling us what the exception type is. And when it comes to like exceptions which are of some .NET or C++ language type, there are two different well-known values which we can use. So we can recognize both C++ and CLR exceptions because they have separate codes. And also what we also have is the pointer to actually the structure called runtime type information, which is like a poor man's reflection. It doesn't allow us to examine the objects completely, but at least it allows us to grab the type of the exception, for instance, in C++. So whenever you need to debug those low-level things, just keep in mind that this cheat sheet may be super useful for you, how to traverse this structure. You just need to go through 4 pointers, and then you get the exception type name like human readable. So this is how we can do on WinDebug level, like super low level on machine code. What happens when we go slightly like to the higher levels? So in SEH, there are actually two different implementations of structured exception handling, depending on the architecture. In 86 or in 32-bit architecture, what we have is a structure based on the stack. So we do have a stack chain of handlers, which we can use to actually traverse the exceptions. Whenever we start the new method and we do try catch, the operating system, or actually the code of our application, just registers new handler in the stack chain, which then is traversed by operating system to see which try catch can use or can handle the exception. So this is why we can see that when we nest multiple try catches blocks one after the other, operating system can go from like very bottom to the very top and see which catch could handle them. This is how it works in 32-bit scenario. In 64-bit, SEH, as well as some other mechanisms like dwarf or intermediate language exceptions handlers, they are based on tables. Table-based means that we do have some metadata describing how the exceptions should be handled and propagated, and we'll actually see this in a sec when we focus on the intermediate language exceptions. But let's stick with SEH, and what we can do is we can see how this works under the hood by creating our own SEH exception, like manually with machine code. So let's make this start a project and run this code. So what we are doing here is we need to put a special structure on the stack, which basically has 2 pointers. First pointer is the pointer pointing to the previous exception handler. So we are in a try-catch block. We are actually in a try, executing some other method. This other method wants to set up another try-catch block. So this new try-catch block must point to the previous try-catch block so it can be traversed later on. So first pointer points to the previous try-catch block. The other pointer is basically a pointer to a method, to our handler. So what we are doing here is we do set up this structure and put it in special well-known place in FS register. Then we again generate some exception. Let's stick with assembler, why not? So we do generate null reference exception here, or null pointer. Like we explicitly assign 0 to some register and we try to dereference it. And then what is happening here now is we do get an exception. We try to read null, so this is not allowed. Our handler is being called. And our handler looks like this. Notable things important for us here is we do get a full details of the exception, what happened. We do get exception record, frame, dispatcher, context record. What is important for us, or what is most useful for us, is this context record variable. It contains all the registers and the state of the CPU at the point of throwing the exception. Since it has all the registers, we can try modifying them. So what we are doing here is similarly to what we did in VEH demo when we modified one of our variables. What we do here is we just modify the CPU register and we increase instruction pointer by 3. Why by 3? Because if we decompile this code and see the machine level, we can see that this move EAX1 is actually 3 bytes long. So we tell the operating system, hey, increase the instruction pointer by 3, and then again, just continue. Everything is perfect, just carry on. Operating system takes the structure, restores it, and then because we increased the instruction pointer by 3, we just skip this instruction, and we carry on. So we land in this puts, and we can see that if we zoom here, it works as a charm. And this is actually how things are implemented under the hood. This is not a trickery we just do here just for fun. This is how things are implemented under the hood. The exception handler is being called. We just need to examine the state. We need to see where we are, what happened, what is the state of CPU, and then effectively just jump somewhere else and carry on. Also, interesting thing here is if you have ever considered or actually wondered, how is it that whenever you access null reference in .NET, you get null reference exception? You may come to a conclusion that .NET must introduce some checks like if this reference is null, throw null reference exceptions, something like this. And you would be very wrong. What is happening in .NET actually, and the same is done in Java and in other platforms, is we want to avoid this code which is expensive. What we do is we just assume there is no null reference here. No reference is correct. So we just take the reference and we just dereference it similarly to what we do here. When we do something like this and we in fact have the null reference exception, the memory management unit kicks the CPU and tells, hey, you accessed invalid memory. Then CPU calls .NET exception handler. Then .NET exception handler checks, OK, I was actually trying to dereference some reference which I assumed was not null, but it looked like it is null now. What do? Just throw new null reference exception. It's even more interesting, for instance, in Java, and probably will work the same in .NET sooner or later, because in Java, even if you do explicitly check for null reference or null pointer, JIT compiler, just-in-time compiler in Java, may ignore this check completely. It will not compile this if for you. The if won't be there. So now what happens? The null reference is being thrown. The MMU kicks the CPU. Java is being notified. JVM checks, OK, I was trying to dereference the reference, some object, and it happened to be null. So what do I do now? I go and check if the user checked whether the reference was non-null. If the check was there, if we explicitly put if reference not null, then what Java does, it just gets rid of the code it compiled, recompiles it again with including the if condition this time. So this is like multiple compilation of the method, something which we'll have or actually already have in .NET platform because we are going towards the multi-tiered compilation. So maybe this optimization will be introduced as well. OK, so that was SEH and in x86 and x64. When it comes to VEH and VCH, those two mechanisms are highly undocumented. It's very hard to figure out actually how they work under the hood. If you want to figure them out, well, in 32-bit application, it's easy. You can find all the handlers by iterating through the whole memory addresses, which takes around 10 seconds at least on this machine. In 64-bit, it probably would take a little longer. You could do some optimizations like check which pages were mapped into the process or something like this. But generally, those things are not very well explained, not even in documentation. If you would like to take a look at those, you probably need to start debugging your operating system kernel. This can be done. You don't need to have two machines right now. You can do live debugging of your kernel of operating system, but then you probably need to read some machine code, so it's not super nice. At the very end, I do have a link which points to some forum where people were actually doing things like this. So if you are interested, take a look at this. Now, going up, intermediate language. So we mentioned that in SEH 64-bit, exceptions were table-based. And the same goes in intermediate language. So what happens is, when we actually execute some code, so when we start with method like this, we have try, catch finally. What happens when we compile this method for intermediate language is we do have some instructions like in the IO language, and all those instructions, they have numbers. You can see in here in the snippet. For instance, this instruction, like here at the top, has number 001. So what is happening is we just specify which lines of code contain which exception handlers. So here at the very bottom, we can see that we do say that instructions from number 1 to number 10, that's a catch block for something. Then we also say there is another catch block and there is another finally with pointers to different instructions. So this is how it works when we say it's table-based. When you do have some exception, .NET goes, checks the metadata, and sees whether that given instruction which from the exception was actually in one of those handlers or not. So now the thing is, interesting thing to notice here is we have quite a lot of instructions like this. Nope, NOP, no operation. And those instructions are introduced by just-in-time compiler when we, for instance, compile our applications in debug mode in order to first simplify the debugging, but also they are sometimes introduced to make the alignment of the code better, then it executes faster. And the question is, because just-in-time compiler in .NET at some point was introducing those NOP instructions in almost all the places to simplify debugging, and as a side note, the question is it safe to introduce this seemingly not harmful instruction in any place? And actually, when we take a look at .NET, there was a nice bug, because previously in some .NET before .NET 4, I believe, the lock mechanism which we were using worked as on the left-hand side of this slide. So whenever we had lock on some object, it was compiled to monitor enter, then try catch block, try finally, and then finally what we do is we do monitor exit. Now the thing is, because NOP was introduced in multiple places, whenever we landed in this line 3 with NOP instruction, we could get out-of-bound exception. So our application could start crashing, and because we are not in the try block yet, the finally was not executed. So if we had situation like this caused the deadlock. And there was this was a real bug in .NET Platform, which was then fixed by changing the underlying implementation to use something like monitor enter, which was atomically setting the flag telling us whether the exception, whether the monitor was taken or not. And then finally, we just need to check this flag. This is especially important because a lot of snippets, either on MSDN or in Java documentation or in any other languages, they typically show you the implementation as on the left side of this slide. Do take the lock, then enter the try block. But if you have no guarantee that there is nothing between you taking the lock and entering the try block, then it may happen that at some point you will get a very nasty deadlock because of code like this. So just beware that things, if you do follow the pattern on the left, it may crash one day depending if everything is fine or maybe if there is some optimization under the hood. Trivia, again, returning in finally. In C#, and IO, it's super easy because it's not allowed. In C++, it's even easier because there is no finally, so we cannot return. But in SEH, in VCH, and in Java, we can do those things, and they work as more or less as expected. Only let's see what is happening in SEH when we do return in finally. So we do go to global unwin thingy. Let's start this project. And what we do here is we start again from main. We go to first try, try catch, second try. In second try, we have try finally. In third try, we do have try finally. But here in the finally, we do return. Generate exception, again, some division by 0 as always. What is happening here in our application is we do enter try 1, try 2, try 3. Exception is being thrown, division by 0. What we do is we go through the stack, we check, hey, is anyone willing to handle this exception? We get to this first try, filter tells us, hey, I would actually like to handle this exception. So what we do now is we start unwinding the stack. So what we do next is we execute the finally in this method, and then we do return. And now things go wrong, because in second try, instead of executing finally again, what is happening here, instead of doing this puts in finally 2, we are actually calling exiting try 2. So we just stopped executing the finally and catch blocks because we just called the return instruction. What's more, we do execute finally normally because it is still in try-catch block, but then we just call exiting try1, and we never call this exception handler. So just by doing return in SEH, we just break the thing, and let's beware of that it may be broken very easily. And the thing which we actually broke is called two-pass exception system. And the thing is the same as in .NET. Whenever we do have exception in .NET, the .NET platform does two passes. In first pass, it goes through the exception handlers and asks them, hey, do you want to handle this, this, or not? Then, when it finally finds the handler to handle the exception, it goes again through the same structure and start unwinding the stack. And here comes the difference between the exception filter and between catching the exception and then rethrowing it. If we do throw an exception and want to check the message, and we do this like on the left-hand side or on the right-hand side, what happens is when we catch the exception and rethrow it, what happens with the code on the left side is we don't have the line throwing the exception. Why? Because we rethrow exception in the second pass of the system, not in the first pass. With the code on the right-hand side, we do the if check effectively in the first pass of the exception mechanism. So whenever this exception is being ignored, we don't lose the stack trace. So exception filters in .NET are not just syntax sugar or whatever else. They are actually super useful because they allow us to handle exceptions completely differently by introducing some code into the first pass of exception system. Now a few words about thread abort. Whenever you call thread abort, it's actually tricky because it's not in .NET Core anymore, so this slide is probably getting outdated super fast. But when it was being executed, what happened is it was setting some nice flags on the threads to actually do some inter-threading communication to throw this exception. So how it worked under the hood, the thread abort was suspending the thread, setting some metadata, and then queuing some piece of code, which was actually checking whether the flag is being set and then propagating the exception. The interesting thing here is because the other thread which we want to abort may actually be doing something useful, maybe working. How do we force it, or how do we convince it to check the flag and throw the exception if needed? And the thing is, .NET was doing something similar to what garbage collector does. It was hijacking the threads by modifying the instruction pointers directly. This should not happen anymore because in .NET Core we don't even have thread abort exception. However, it's nice, a very nice piece of history. When it comes to very nasty things, like exceptions which we cannot handle, one of them is access violation. And depending on how we throw this exception, we may get completely different behavior. Because if we start writing on a null pointer partition, the same way I told you about how .NET checks whether there is a null reference or not, depending how we access this part, this piece of memory, may cause completely different results. So if we write to that place directly using some native code, we may actually generate exception which is not mapped to null reference exception, which is mapped to access violation exception directly. So we may get this exception depending on which methods we use, and the thing is different .NET APIs, for instance, write byte versus copy, they may use or may not use the native code and the managed code. So they may work completely differently when it comes to accessing the wrong or invalid memory. And what happens with access violation, depending how it comes, we may not be able to catch it. And the thing is, we were able to catch it previously, but are not able to do it anymore. And in .NET 1.1, there was actually, in .NET 1, there was no access violation exception at all. Again, in .NET 2, there was an exception, but we could handle it. Now, we cannot handle it. It depends on the configuration. And the interesting thing here is, if you ever imagined, is it possible that only some of your finally blocks are being executed? This is what can happen with access violation. Because when access violation is being thrown, only methods marked with the special attribute called HPCSE, handle process corrupted state exception, only try-catch handlers in that methods are being executed when access violation is being thrown. So it may happen that even though you do catch the exception, half of your application is now completely broken because finally and blocks were not executed, locks are not released, and all those things. So even if you do catch those exceptions, just beware that it may be safer to just stop doing, stop working, just kill the application, save the state, and turn off everything. And finally, just to wrap up this presentation, we started with a very nice case of Stack Overflow exception, which we were unable to handle. So now let's do it in .NET. So how do we handle the Stack Overflow exception? And to do that, we will actually use all the things we learned during this talk. So we learned about low-level mechanism called SEH or VCH. We learned about things that we can modify the registers. We learned that we can generate some machine code in .NET. And all those things, if we put them together in this very simple demo, what we can do is, let me just start this application so it's preparing to throw the Stack Overflow exception. What we are doing here is, I do have a very simple method called doWork. And this method doWork, what it does, it just goes and in infinite recursion calls itself to generate Stack Overflow exception. What I do in this application is I register the VEH exception handler, and I want to follow the set jump, long jump approach to handle the exception. So with this handler, I want it to be called when the exception is being thrown. But before I call this doWork method, I execute some machine code to persist all the registers I have. So EAX, ESP, BP, all the crucial registers I need, and then I call the method. So doWork is now being called, and then when doWork causes the Stack Overflow exception, my handler is being called finally. What I can do now is I have all those 4 parameters which we have seen in SEH demo, so I do have access to all the registers. I can check the exception code, I can restore the registers, and then effectively do the jump to the place which I know is safe, and effectively this place is here to the return instruction. So I generate some machine code, register all the handlers, do the set jump, long jump approach, and ultimately when I call my function, I can handle Stack Overflow exception, and ultimately I can write successfully, I am done. So this is how we can do this. Obviously, this is probably not something you want to do in your production code. It only shows that you can do this if you do understand all the mechanisms of exceptions under the hood. Just to wrap up, probably for .NET developers here, the most important thing is whenever you do async await, always await all your tasks. Do not use async void. If you do use async void, make sure that you handle all the exceptions. Handle all the unobserved exceptions from tasks, and do not create threads with unhandled exceptions. Apart from that, if you are just playing with exceptions, at some point think about them. Think what it's better when those severe exceptions happen, whether it's better to crash the application, or maybe there is something you need to do, save the state, protect the user from breaking its context, application, whatever else, and then maybe just terminate. Always consider whether it's safe to continue. Having said all of that, this QR code points to this slide deck, and now it's a Q&A time. Any questions? Yes. Okay, 2 questions here. First question, or second question, let's start with the second one, was we do have an exception. There are generally 2 approaches, whether either if something goes wrong, we throw exceptions to the higher layers, or instead of like throwing exceptions, we can return some error codes showing what was happening. I would add to that there is another exception, which is based on, for instance, optionals, which is like very popular in functional programming. The question is, which one exception is better, faster, generally, which should be followed? There is no definite answer for that. Depending on the platform, for instance, like if you work with low-level languages, C++, assembly, you probably just return the code. If you work with higher-level languages, throwing exception is OK. There is one thing I would add to that. It depends who calls who. Because if this exception is being called from some external caller, like this is RPC or something else, don't throw the exception because then you kill yourself instead of killing the caller. So in that case, return the code. But if you do propagate the exception in the same process or something else, it's a bit safer to kill yourself because at the same time you kill the caller. So the caller is like in need of handling that. The previous question was about comparing performance of exception filters and normal catch with if condition. I don't know if there is a difference, never measured it. To be honest, I would be a bit surprised if there was a significant difference, but my guess would be exception filters should be faster. But I never benchmarked this, so I cannot give a definite answer. Cool. Any other questions? Yep. The question is VEH used by CLR? As far as I understand, only SEH is used by CLR. So .NET exceptions mechanisms are based on SEH. I don't know how it is working in .NET Core, depending on the platform. I believe for Windows platform, it should be the same. For Linux platform, it may work on signals. But I never saw .NET using VEH handlers. I'm not saying they are not used, but I did not find any usage of those. Cool. If there are no more exceptions, there is.
So from a performance perspective, is that
Is the question, do we always want to catch everything? OK. OK, why is it bad? It's not necessarily bad. The thing is we should not catch everything on like the bottom layers. We probably want to catch everything on the very top layer, like in your controller or somewhere else. In that place, just log the error, save the state, and probably crash the application if this exception wasn't handled down the stack. Handling all the exceptions may be very harmful when doing this at the bottom of the stack, like in deep goals. OK, any more questions? I don't see any more questions. So let's quickly wrap up with references. If you are interested in the things I showed you today, a few things, some books if you are interested in, like CLR via C#, .NET Internals, Cookbook, depending on which area you are interested in, those books may be super useful for you. If you are interested in the things like in the way I presented them to you, there is a great blog called The Old New Thing, which shows you a lot of architectures or low-level system mechanisms if you are interested in. If you want to see the things I showed you today again or read them on my blog, here are some links you may be interested in reading. If you want to read the same things or read about exceptions generally, but outside of my blog, there are also some more links which I would like to show you. So here are some places you may start your journey when reading about exceptions of very, very different architectures. And having said all of that, I think it's all what I wanted to tell you. So my name is Adam Furmanek, and I'd like to thank you for attending this talk. I hope you enjoyed it. Thank you.